All right, in 4.5, we're going to learn a method called substitution. A lot of times it's called u substitution because we use this variable u. Um, but we're going to use substitution to take more and more complicated looking integrals. The key to it, though, is recognizing that as complicated as they might look, they're all going to come back to looking like one of these five, and possibly a couple more. There's a couple more that we hardly ever see. I'll write them down later, but um, they're gonna look always like one of these. They're gonna come back to one of these, and this is a short list. And I would say 75% of the time, it's going to be this function that you're going to try and get it to look like. At this level in 4.5, this is the major one. It's just x to some power times dx. It's going to look like this. Okay. And how do we take the antiderivative of this? It's pretty simple. We know that, or we'd better know that this function that we get as the answer, when we take the derivative, this is what we get. We know there's that connection. Antiderivative goes this way, derivative goes this way. So if I were to take the derivative of some function and get a power of n, I know that came from subtracting 1, so I will add 1 to take the antiderivative. And I know I'm going to multiply this n plus 1 out in front. It's going to become the coefficient when I take the derivative. Well, the coefficient here is 1, not n plus 1. So we need to fix that. So we put 1 over n plus 1 to cancel out that multiplication of n plus 1. N plus 1 over n plus 1 would be 1. And then we add c. And then each of these has their own antiderivative. The function that has a derivative of sine is, we might think cosine. We just remember that the derivative of cosine is negative sine, but this is positive, so we'll put a negative here. So the derivative of cosine is negative sine, and then we make that negative, making the overall thing positive. This here, the antiderivative would be sine. The derivative of sine is cosine. This one here is the derivative of tangent. This is the derivative of tangent, so tangent is the antiderivative of secant squared. And this is the derivative of secant. Okay, and there's even a couple more. So there's the other two. But that's it. That's a comprehensive list of the types of functions we know the antiderivative for. And like I said, this one's going to be the major player in the whole thing. And whether it's x or u, it doesn't matter. If I change what the name of the variable is, it doesn't change the fact that this would still be 1 over n plus 1 times u to the n plus 1 plus c. That'd be the same thing. It's just that in calculus, antiderivatives and u have this special little relationship. Okay, we could just as easily use w or a or n. It doesn't matter. It's just the letter we choose because it's not n. We use n for powers. It's not x. We use x for variables. We just happen to use u to represent what? To represent an entire function. X is just a variable. It's this thing that could be any number. U is something we use to represent an entire function. A function of x, meaning that it's not just x to the n, it's x squared plus 2x plus 5 to the n times the derivative of that. Okay? Let me show you an example of one that we can pretty easily see. Okay? So let's take the antiderivative of x to the third plus 2, and we'll take that to the second power, and then we'll multiply that by 3x squared dx. Okay, so taking the antiderivative of this looks pretty daunting. You're at a loss of what to do, what to try. It becomes pretty simple, though, when we recognize that this is true. If I have a something to the n times the derivative of the something, it should play out like this. This should be the antiderivative. So if I let this be u, and this be du, first of all, if this is u, then this is du. This is the derivative of u. 3x squared plus 0, okay, times dx. So now this becomes the antiderivative of u du. All of a sudden it's a lot easier. Not u, but u squared. So, hey, u squared du, I can take the derivative of that. I can just take this to the third, multiply by 1/3, and add c. That's it. The only thing is that u is standing in the place of x cubed plus 2. So in the end, it becomes x cubed plus 2 to the third power multiplied by 1/3 plus c. Now, if we were going to do this any other way, without u substitution or a really keen eye, we would have to just multiply this out, right, and then distribute this 3x squared, then take the antiderivative of each piece, and we probably wouldn't even recognize that it could be factored this way. But with this, with u substitution, recognize that I see a function and its derivative in the same integrand. It makes it so easy. I just need to recognize that fact, that pattern, and then anti-differentiate and replace u. Or don't even replace u. Just recognize that this is a function and this is its derivative, and you can go straight to here without writing this step if you're really well practiced at it. But this works for whatever. And we're going to make some few adjustments. We're going to make it fit sometimes in the practice problems. But for the most part, we're going to get things to look like u to a power du, and to a lesser extent, these, and to even a lesser extent, these, and to an almost non-existent extent, these. Okay? So it'd say like 75%, 20%, 4% and 1%, I don't know. It's just going to be this for the most part. So now that you have a general idea, we're just going to recognize things as u and its derivative, or the sign of a function times the derivative of that function that's in the sign. Then we're going to anti-differentiate with respect to u and replace what u was. Right? This is basically the counterpart to the chain rule. If I were to take the derivative of this, I would need to use the chain rule. In fact, we could take the derivative of this. 3 times 1/3 would be 1, okay, times x to the third plus 2. Then we'd subtract 1 from the power, but we need the chain rule because we have a function inside a function. So we get 3x squared dx. And that's it. That pretty much wraps it up. I'll see you in the practice problems video. Thanks for watching.